So yesterday, we discussed the dynamics of space-time. And as somebody asked, how do we know that when we have this, this action that we chose to introduce? So we chose to introduce this action, the Einstein-Hilbert action, with essentially a Lagrangian density, which was the Ricci scalar. How do we know that this actually corresponds to physics? Well, first of all, we need to reproduce Newtonian gravitation in some certain limit. So that's what we will do today. Then, of course, we need to go out and do measurements in the real world, to see whether or not the predictions of applying this action actually is what we can observe in the real world. And as it so happens, to date, it's been that way. So what we will do today then is we will go into what is called the weak field limit. And as the name suggests, what we will do is to see how Einstein's equations behave for weak fields, which is when we expect to recover Newtonian gravitation. So what does it mean for a field to be weak? Well, if you look at special relativity, there the metric is the Minkowski metric. And so we define a weak field to be any set of any manifold where we have a metric that takes the following form. So we're going to have a metric G mu nu, which is the Minkowski metric, but with a small perturbation, H mu nu. So H mu nu here, the components should be much smaller than 1. So H is a small perturbation to the Minkowski metric. Now, what we will then do is that we will proceed to go through everything that we've done so far. So we will derive the Christoffel symbols, we will look at the curvature tensor, and finally we will look at the Einstein field equations linearized in this perturbation H. So we will only consider terms linear in H, and we will not consider any terms that are H squared or above. So we are going to linearize the entire formalism. That is, we're going to ignore terms that are order H squared. So anything that contains an H squared or higher, we are going to throw away. So just as an example, if we want to consider the inverse metric, so G mu nu, that's going to be equal to, well, the inverse Minkowski metric minus eta mu sigma eta mu rho H sigma rho plus higher order terms in H, so order H squared, and we define this to be eta mu nu minus H mu nu with the indices upstairs plus these higher order terms. So we're going to raise indices of H just using the Minkowski metric. So we can check that this actually makes sense, that two linear order in H, the inverse metric is given by this expression. So what we want to have is G mu nu, G mu lambda. This should be delta nu lambda, right? Because it's the metric and the metric inverse. So if we write down, if we take this expression that we had here, and we insert it, or rather, let's take this expression that we already had. We have eta mu nu minus eta mu sigma, eta mu rho, h sigma rho, plus order h squared. And then the metric was just given by this. So eta mu lambda plus h mu lambda. So now eta here multiplied by this is just going to be terms of linear order at maximum. So the first ones together, that's just delta nu lambda because of the properties of the Minkowski metric. And the second one is eta mu nu h mu lambda. For the second term here, when this multiplies anything that's there, well, this multiplied by this is linear in H. So that's a term that we should include. And we get minus eta mu sigma, eta mu rho, eta mu lambda, h sigma rho. However, when I multiply this by this, I get something that's order h squared. So I'm just going to bake that into the order h squared term. Of course, when I take this order h squared term and multiply it by this, I also get something that's order h squared. Now in this last term here, we have a sum over mu. So performing that sum, just write down what we had before. Performing that sum, that's delta sigma lambda. So what we get is eta nu rho h lambda rho. So this is just a few renamings of indices and a few symmetry transformations away from being equal to the middle term here. So what we do get here, well, plus order h squared. So these two terms cancel. So together we find that this is equal to 0. So what we end up with is indeed delta nu lambda to linear order in H. So indeed, two linear order in H, the inverse of the metric, is exactly given by this expression. Any questions? Okay, so I mean, this is just a linearization. So we can do the same thing when we're considering the Christoffel symbols. So one thing to notice here is that when we compute curvature, if you remember the expression for the curvature tensor, I'm not going to write out the indices here. I'm just going to write something schematically. We had some derivatives of the Christoffel symbols. And then we had something similar just with different indices. And then we had here something that something like the Christoffel symbols squared. again, matching all the indices correctly. So what we can note here is that if we compute gamma, it's going to be linear. In H. So we're not going to have any terms at leading order. So the reason for this is that if we look at gamma, so let's look at mu nu lambda, it's 1/2 g lambda sigma d mu g sigma nu plus d nu g mu sigma minus d sigma g mu nu. So the point here is that if we look at these derivatives, and we remember now that g was equal to the Minkowski metric plus the perturbation. The Minkowski metric, all of the components of the Minkowski metric are constants, which means that all of these derivatives are going to be linear in H. So that means that the Christoffel symbols are linear in H. They have no contribution from the first order, from the zeroth order in H. So that means that if we look at the curvature here, gamma squares are going to be of order H squared. So they're not going to be relevant for computing the curvature to linear order. Instead, we're going to be left with these that are linear, that the gammas themselves are linear in H. So we're going to be ending up with some second order terms. Sorry, some first order terms, which are second derivatives of H. Because if we look now here at the Christoffel symbols, since this parenthesis was linear in H, I can forget about any H terms in this inverse metric, because any H terms here are going to multiply this term, which was linear in H, and then therefore going to end up being quadratic in H. So this is equal to 1/2 eta lambda sigma, and then d mu H sigma nu plus d nu H mu sigma minus d sigma H mu nu. So all of the H dependence is inside of those derivatives, plus again higher order terms in H. So these are the Christoffel symbols, therefore. So I'm not going to go on explicitly, but just remember that when we compute when we compute the curvature components, this is going to be equal to those derivatives, as we said. So we have d lambda gamma mu sigma nu minus d sigma gamma lambda nu mu plus higher order terms in H, which we're going to ignore for the time being. So using this and just going on and on, we can compute the Einstein tensor, which is what's later on going to enter into the Einstein field equations. So if we just take the linear contribution, this is going to be ending up to be 1/2 d nu d mu H. I should use the same indices as I used in the lecture notes, or I'm going to confuse myself. H mu sigma minus, and then we have the D'Alembertian H mu sigma. We'll come back to the expression for the D'Alembertian here, minus d nu d sigma H, and I'm also going to come back to what H is, plus d sigma d mu H mu nu. So here we have two things that we've not seen before. We have this D'Alembertian and we have the scalar H. So this D'Alembertian, that's just eta mu nu d mu d nu. So it's the regular wave operator in Minkowski space, essentially. Whereas this scalar h is just a trace of the perturbation. And again, since we raised the indices using this inverse metric, and since this inverse metric, the only non-linear part here is this eta, essentially we can raise raise and lower the indices of h just using the Minkowski metric. So this would be equal to eta mu nu h mu nu. So it's essentially the trace of the perturbation. Any questions so far? Oh no, I see. I copied the wrong the wrong expression here. Of course I did. So this is actually not the case. This was the curvature tensor, or rather this is R mu sigma. So this is the Ricci tensor. The actual expression for the Einstein tensor is a little bit more complicated. Let me just write down very quickly. The mu h mu sigma, I mean, it's the Ricci tensor, and then minus this thing with let's see, did we get it correctly? That is that term, that is that term, that is that term, plus the sigma mu h mu nu. So that's the Ricci tensor. And then we have plus eta mu sigma, and the D'Alembertian acting on h. So we have those 5 terms. Did I get the signs correctly too? I hope so. Otherwise, I mean, the expression is also in the lecture notes. Again, plus higher order terms in h squared. So this looks rather intimidating. This is essentially a differential or a second order differential of all of the components of this perturbation. So we're going to need to simplify this somehow. However, there is one thing that we have not really talked about so far, and that's gauge fixing. So let me just charge the pen. So you may also be familiar with gauge transformations in electromagnetism. Essentially, we can change the 4 potential by the derivative of a scalar, and we will end up with a new 4 potential that is a priori different from the previous 4 potential, but it gives the same electromagnetic fields. So we have something similar in general relativity, which is that we can make coordinate transformations. So we can have different coordinates that describe the same manifold, essentially. And what we're going to do is that we're going to look at infinitesimal coordinate transformation as gauge transformations. So what I want to say is that we can make coordinate transformations they're essentially given by vector fields. So x prime, mu prime, or just mu, which is the original coordinates plus plus the components of some vector field psi. So this is an infinitesimal coordinate transformation as long as this psi is small. And as long as the metric was of this form, so with a small perturbation here, h mu nu, then as long as chi is small, this small coordinate transformation is again going to give you a weak field metric. It is of the same form. So the question is, how can we deal with this? So in the same way as we can deal with this in electromagnetism, we can fix gauge conditions such as we can use the Lorentz gauge, for example, or the Coulomb gauge to fix the potential and the vector potential of the electromagnetic fields. We can introduce gauge conditions in general relativity to fix what kinds of coordinates we are looking at. So the one we are going to look at now is called the harmonic gauge. And harmonic gauge is when we have when we decide that we should have a coordinate system where the coordinate functions themselves satisfy the wave equation, essentially. There will be some gauge freedom left once we have done this, but we'll come to that later. So it's an exercise in the lecture notes, so I'm just going to write it as an exercise here as well to show that this implies the following. So this should imply that G mu nu gamma mu nu lambda is equal to 0 for all lambda, which leads to a condition for the perturbation h, which is going to be that if we take the mu h mu lambda, this should be equal to 1/2 d lambda h. This is essentially the linearized version of this, once we have written down what the Christoffel symbols are. So we leave that as an exercise. But if we use this, we can look at the Einstein tensor here, and we can use it to rewrite everything that's in here on a slightly simpler form. So what we're going to get is that G nu sigma is going to be minus 1/2, and then the D'Alembertian acting on h nu sigma minus 1/2 eta nu sigma, and the D'Alembertian acting on h. Well, again, plus higher order terms. And according to Einstein's field equations, this should be equal to 8 pi multiplied by Newton's constant times T nu sigma. Or in other words, if we just do the following, we take the D'Alembertian out, and it acts on h mu nu minus 1/2 eta mu nu h. That should be equal to 16 or minus 16 pi g t mu nu. So just looking at this, we can introduce a new notation for this. I'm going to call this h bar mu nu. And this is also called the trace reversed perturbation. And if you look at the form here, you can understand why. So if you take the trace of this h bar, so h bar mu mu, that would be h mu mu minus 1/2 times 4, because the trace of eta is 4, times h, which is just h minus 2h, which is minus h. So it has the opposite trace of h, and the off-diagonal terms are all the same. So this is called the trace reversed perturbation. So what we had here was that all of this was equal to the D'Alembertian acting on the trace reversed perturbation. That being said, then, this looks kind of familiar, right? If you remember now, if I just look at the Minkowski coordinates, or rather the background coordinates here, because we had that the coordinates were essentially Minkowski. We had the metric was essentially Minkowski, I mean, apart from this small perturbation. So let's call the coordinates t, x, y, and z. Then what this is essentially dt squared minus Laplace squared acting on h mu nu bar. So what we have here is a wave equation. It's a wave equation where the wave speed is the speed of light, which we have put to 1. And the source term is this energy momentum tensor. So this is kind of already telling us that at some point we're going to have waves here in these perturbations, and that is exactly what we're going to do later when we study gravitational waves. But that's now getting a little bit ahead of ourselves. Our aim at this moment is just to recover Newtonian gravity in some limit. Okay. So the question is, what is that limit? So in order to recover Newtonian physics, I mean, there are essentially two things that we need to go back to. First of all, well, we know that if things go very, very, very fast, Newtonian physics no longer hold, because even without gravity, we are going to need special relativity at some point. So the Newtonian limit it's going to involve two main assumptions, where one is that things move slowly. And that is going to boil down to that the energy momentum tensor is going to be dominated by the energy density. So T mu mu is dominated by the 0,0 component, so the time component. So this is going to be T00, which was just the energy density. And the energy density in the slow-moving regime, where we have no, where gamma factors are close to 1, that's just the mass. So what we're left with is going to be essentially the mass distribution, where so rho here is going to be, in essence, the mass density. Okay. So the second requirement is that things are not incredibly heavy. So the mass densities is small. So if this is not true, then of course we are no longer in the weak field limit. And you know this because you've seen the Schwarzschild solution. However, as long as the mass density is small, we're going to be able to look at something that's close to Minkowski space. Okay. So those are our assumptions. So let's look at what this does to the case we had. So everything is now going to be dominated by the 0, 0. So I mean, if we look here at this equation, if the only relevant component of t is the 0, 0 component, if we look at any other component, the left-hand side just is 0. So that's then going to be solved by h bar being 0, for example. However, the component we can't solve by just letting h bar be 0, or the corresponding component of h bar being 0, is the 0, 0 component. So let's insert that here. So the 0, 0 component of the Einstein field equations becomes, so what we had here was, well, it becomes the following. We have the 0, 0 component of h bar. And assuming now that things move slowly, that this then this h is going to change slowly, which means that the time derivatives of h are going to be small. So in that case, these time derivatives are negligible, and we are left with minus Laplace h bar 0, 0, which should then be minus 16 pi g times the mass density. Now this looks kind of familiar, right? So recall the following. Recall the Poisson equation. For the Newtonian gravitational potential. Newton's gravitational potential phi. So that is given by Laplace phi equals to 4 pi g rho. So this looks rather similar to this thing. In fact, it looks exactly like that thing, and that's exactly what it is. So what we can now identify is that we identify the Newtonian gravitational potential with, let's get it right, with 1 over 4 times h00 bar. Or in other words, h00 bar is 4 times the Newtonian gravitational potential in this case. Right. So this also means that if we take the trace h bar, so this is the trace of the trace reversed perturbation. This is going to be h bar 0, 0, as only the 0, 0 term was relevant, and because the Minkowski metric is what it is equal to h bar 0, 0. So this is also 4 times the Newtonian potential. So it follows that if we look at the perturbation itself, so h mu nu, that is h bar went up there, h bar mu nu minus 1/2 eta mu nu h bar well, h bar. This is 4 times the Newtonian gravitational potential, delta 0 mu, delta 0 nu, minus 1/2 eta mu nu. Or if I want to be more explicit, the 0, component of the perturbation is 2 phi. Because if we insert 0 here, well, 0 and 0, this is 1. And the 0 here is 1, 2, so we get 1/2 in total. And 4/2 is 2, so that's where this 2 comes from. If we look at Hij, these components are 0, because the spatial indices are not equal to 0. And this is minus 1. So again, we end up with a perturbation which is 2 phi delta ij. So it's 2 phi if I is equal to j and 0 otherwise. So our metric, or line element in this case, is going to be given by 1 plus 2 phi dt squared minus 1 minus 2 phi dx squared, where these t and x, they are the standard Minkowski coordinates. So we end up with this small perturbation, and of course here's where the requirement that the mass density is small comes in. That we should have a small enough Newtonian potential for this to actually be a perturbation of the metric. So this is the weak field stationary limit. So apart from the assumption of having a weak field, we have assumed that T mu nu is dominated by the mass density, and that things are moving rather slowly. So this is geodesics in this space-time. So geodesics in the above space-time. And I'm now going to assume that we're going to be outside of this mass distribution. So we can look, well, let's just look at the Newtonian potential outside of a point mass, essentially. And you know that then, if it's essentially that we have the sun in the middle, and then we're going to have something which, at least in Newtonian mechanics, are elliptic orbits around that. So let's see how we can recover that now to leading order. So what we're searching for are the geodesics, which should, if we write down the L, what we want to look at is the following. And we want to integrate this with respect to the curve parameter of the corresponding world line. So if we write this down, it's t dot squared 1 plus 2 phi. And phi here depends only on r, as long as we have a spherically symmetric mass distribution. Minus 1 minus 2 phi of r. And then we have r dot squared plus r squared phi dot squared. So I'm now considering only motion in a single plane. So I've arranged my plane so that I have theta equals to pi half. If I look at the t, at the Euler-Lagrange equation for the t coordinate now, what I end up with is that dds, so nothing here depends on t explicitly, so I'm only going to have the dds term. I have t dot, I have 1 plus 2 phi, So if I do, and this should be equal to 0. So this means that t dot 1 plus 2 phi is a constant. And as long as I'm constraining myself to slow-moving objects, objects moving much slower than the speed of light, this constant is going to be equal to 1. So this is going to tell you that t is equal to the proper time mass. So this is what we expect for an object in Newtonian physics, that t, the proper time, is actually the time coordinate, right? Well, there should be an approximate here, but as long as this potential is much smaller than 1, we're fine. If we look at the phi coordinate, again, nothing here depends on phi explicitly. So what we end up with is that dds, which now is the same thing as ddt, of minus r squared phi dot is equal to 0, which means that we have a constant of motion, which is just what we had inside here. So r squared phi dot, and that's our regular angular momentum per unit mass. And finally, for the r coordinate, we would have the following. We would have, let's put 1/2 in front of everything. So d ds, dl, dr dot, minus dl, dr, because now we have things that do depend on r. So this is minus dds, 1 minus 2 phi, r dot. That comes from differentiating this here with respect to r dot, minus phi prime t dot squared plus r dot squared plus r squared phi dot squared plus r phi dot squared. Now, if we look here at this expression, again, the same thing as we did here. Assuming that this object is slow moving, then the changes in the spatial coordinates are going to be negligible compared to this t dot. And the t dot, we saw that it was 1. So then this entire parenthesis is equal to 1. And it's the Euler Lagrange equation, so this should be equal to 0. So this is going to be approximately, if we go through everything, is going to be approximately minus r double dot minus phi prime plus L squared divided by R squared. And we set that to 0. And if we just solve here for the second derivative of R, we have that this is minus phi prime plus L squared over R squared. So this is the standard Newtonian expression for motion in the central potential. So we have the radial force, so minus the derivative of the potential, and we have the angular momentum barrier. Okay, so welcome back. So what we did the last hour was we were discussing the weak field limit, and we were also discussing how to recover Newtonian, the Newtonian gravitational model essentially from that. However, on the way, we saw the following pop up somewhere. We saw that we had the wave equation essentially with some source term here for this trace reversed perturbation h bar. So this already hints at us having gravitational waves. because essentially this tells us that there are going to be perturbations that satisfy the wave equations, particularly the wave equation in vacuum when the energy momentum tensor is 0. So this hour we're going to focus on that, and also on what this is going to mean for observers that are inside of a gravitational wave. So that's the topic, gravitational waves. Not to be confused with gravity waves, which is something completely different. Although in Swedish, they tend to be called the same thing. So again, what the weak field limit gave us was the following. We had that that inversion acting on the trace reversed perturbation was equal to minus 16 pi g t mu nu. So this is a wave equation. Now, what we're going to look at this hour is going to be plane wave solutions in vacuum. I mean, much like you can look at electromagnetic plane waves in vacuum, you can look at plane wave solutions in vacuum for gravitational waves. So essentially, that is going to be something like having a perturbation, or trace reverse perturbation, which is given by some amplitude, a mu nu, and then having something like e to the I k dot x. Now, remember, we are working essentially in something that's almost Minkowski space. So this thing here, k dot x, actually makes some sort of sense. Now again, I mean, just like in electromagnetism, this would be complex. If you want the real part or the imaginary part, you can just take the real or imaginary part. If we just insert this in the wave equation in vacuum, so vacuum, of course, being that T mu nu is equal to 0, we're going to end up with the equation k squared h bar mu nu equal to 0. I mean, in order to have anything interesting at all, h must be different from 0, or at least some components of h must be different from 0. Otherwise, we would just have Minkowski space. We would have 0 amplitudes, which would give us back Minkowski space. So this means that the non-trivial solutions in general require that k squared is equal to 0. So this means that this plane wave must have a null wave vector. This essentially already tells us that gravitational waves travel at the speed of light, because the wave vector is a light-like vector. So with that, let me also say that there is also, we introduced the previous hour, we introduced this harmonic gauge condition, which was that, so the harmonic gauge gives that the coordinate functions satisfy the wave equation, essentially. Now, this gauge condition does not completely fix our gauge. So this does not completely fix completely fix the gauge, because we can still do coordinate transformations here. We can still do x prime mu equal to x mu plus xi mu if this xi also satisfies the wave equation. So there is some additional gauge freedom available here. So we can now introduce a gauge, or rather we can fix the gauge. Gauge, or now let's put it this way instead. We do the following gauge transformation. So specifically, we let xi mu be some amplitude multiplied now by the same wave, the same kind of wave phase as we had for the gravitational wave itself. Now, if we do this, so given this, or rather we can, let's put it this way, we can choose B now. Since this satisfies this condition, again, since K is light-like, this condition is going to be satisfied if we choose psi like this. So given that, we can choose B freely. So we can choose the amplitude here freely and still satisfy the gauge conditions. Using that freedom, so in particular, we can choose B such that if we look at the amplitudes here, we can fix those some of the components of those amplitudes. For example, we can fix it such that A mu mu is equal to 0. So the trace of A is 0. And that if we look at the time components of A, so A0 mu essentially, that is also equal to 0. Now, since A is going to be symmetric, because the metric is symmetric, this of course also means that A mu 0 is 0. Okay. So we have used the additional gauge freedom now to choose this particular form of A. However, the harmonic gauge itself, if we look at what that was giving us, we had that d mu h bar mu nu. If we look back here, essentially that this is equal to that gives us that if we look at h bar instead, that's essentially going to say that this derivative is equal to 0. So if we insert this plane wave solution into this condition, which follows from harmonic gauge, this means that A mu nu K mu is equal to 0. So that's what the harmonic gauge gives us essentially. So what I'm going to do now is that I'm going to take a plane wave and I'm going to arrange my directions so that, look at a plane wave traveling in the E3 direction, so in the Z direction essentially. then I know if I look at my this amplitude, I know that all of the time components are going to be 0. That followed from choosing B here such that the trace was 0, well, in particular that A0 mu was 0. So what remains is to look at what should go in here. Now, if I choose the wave traveling in the 3 direction, then K mu is 1, 0, 0, 1. So this means that the time component is 1, the x and y components are 0, and the z component is 1. But since all of the 0 components here are 0, when we look at this condition, the 0 component here is going to go with a 0 something component. So that's not going to contribute. The only thing that's going to contribute is the 1 term here. And it's going to multiply one of these terms. So when we look at what we get out of harmonic gauge, we also find that all of these terms are going to be 0 as well. So we are left with 4 entries here, but this gauge condition, or rather this particular gauge choice, gave us that the trace must be 0. So that means that whatever stands in this position, and I'm going to call this A plus, this constant, must be equal to minus what is in this position. So this is going to be minus A plus. And it will be clear later on why I've chosen the subindex plus. At the same time, the metric is symmetric. So that means that whatever's here in this position must be the same as is in this position. So I'm going to call that A cross. So in this amplitude, I have 2 degrees of freedom. I have the degree of freedom A plus, and I have the degree of freedom which I call A cross. So this corresponds to when I look at electromagnetic waves, I have 2 different polarizations. I have the polarization which is, both polarizations are going to be perpendicular to the direction of motion, and we have 2 such directions. And it's a similar thing here, except that in the electromagnetic case, those 2 polarizations are related by a rotation of 90 degrees. In this case, those 2 polarizations, the polarization which has an amplitude A plus and the polarization which has the amplitude A cross, are going to be related by a rotation in the xy plane of 45 degrees. And you can see that because if you make a rotation of this matrix, which is 45 degrees, this is essentially putting a rotation matrix on either side, you're going to end up switching the position of A plus and A cross when the rotation angle is 45 degrees. So this is essentially the different plane wave solutions that then exists for a plane wave moving in the 3rd direction. Of course, you can also have a linear combination of this plus polarization with a cross polarization as well. Just as in electromagnetism, you can have linear combinations of left and right polarized light and so on. So the question is now, how does this affect stuff? How can we know that we are inside the gravitational wave, and how can we detect it? So in order to answer that, we're going to study something that's called geodesic deviation. So geodesic deviation. So this will require a bit of introduction of concepts. So what I'm going to do is that I'm first going to draw a little picture. So I'm going to take here something that is some sort of simultaneity. So it's a space-like surface that we call simultaneous for some coordinate choice. So for example, when we had the weak field limit, we can say that the same t coordinate in that limit, so the same t coordinate in that Minkowski frame essentially, is going to be defining what is at the same time. Then along this, this simultaneity, we can take two events, or we can take a number of events. So we can take essentially a curve here in this space. And given that curve, we can take the normals to this space-like surface. And then we can create a family of geodesics by looking at how these how the geodesics essentially with those initial vectors here as tangent vectors, how those geodesics would evolve with time, or rather with the curve parameter. So this creates this family of geodesics. So if this was a curve now in this spatial surface, this family of geodesics is going to create a two-dimensional sheet in the space-time. And we can introduce coordinates on this sheet by saying, first of all, if we look at this point, we call this s equal to 0. And then we follow that geodesic for some proper time t, and then we will end up at this point. So this would be the point 0 t. We can do the same thing for s equal to, let me take this one because I need some space to draw. Let's call this s equal to s0. So I'm following now this curve to the point where s equals to s0. And then I can follow that geodesic for the same proper time t. I might end up at this point. So this means that this point would be S0t. So for a given t, for a fixed t, I will have some new surface here. It might look something like that, where the s coordinate, so the if I looked at this fixed t, I of course get the line, I get a curve again, and the s coordinate that parameterizes this curve is going to be essentially the curve parameter, and it's going to be based on where on this geodesic I have to be in order to end up at the corresponding points. So we can now consider now two nearby points here. So I'm going to take two nearby points, and they're going to be separated by some vector x. So some displacement x. It's a small displacement. So this x is essentially going to be the tangent of the curve in the original simultaneity. However, when I go to the time t, I also had this curve. And I'm going to define the vector field x now such that this vector is x. So this is essentially the separation. So here x is the separation between the points that this point and this point traveled to when we evolved the geodesics forward in time. So this is going to define a vector field along this family of curves. And what I want to look at now is essentially how this vector field changes when we increase t. And in particular, I want to look at the second derivative, because the first derivative, essentially we're going to have to define on the on this line here. So I want to look at the second derivative. And the second derivative, well, since it's a vector field, we will have to use the connection in order to describe this. So I'm going to define here x dot dot as the second derivative in the direction. If u here is the tangent of the geodesics, I apply this to the vector x. And if we use now the facts that that we have torsion freedom, and that essentially x and u are going to be, if we define the coordinates on this sheet like this, x and u are going to commute. And furthermore, u is a tangent of the geodesic, so nabla u is equal to 0. If I use all of these things, I'm going to be able to rewrite this as r ux acting on u. So essentially, this is directly related to the curvature of this space-time. So this second derivative of x is directly related to the curvature in the space-time. And inserting these 4 velocities of the observers following these geodesics 2 times, and inserting this x, this displacement between the observers in the second argument here. So if I write this down in components, we have x dot dot mu is going to be equal to r mu lambda sigma nu u lambda u sigma x nu. So this is a bit of general framework, let's say. So the big question is now, if I had this separation here, time equals to 0, what is the separation here between those 2 observers following geodesics? And we want to apply that to our case of these observers being inside of a gravitational wave. So what we are going to do is that we're going to place 2 test particles inside this gravitational wave, and we're going to assume that they are slow moving, so that this u is essentially just the time direction. So for our gravitational wave, we're going to put place the test particles with initial 4 velocities given by u equal to dt. So this of course means that u0 is equal to 1 and ui is equal to 0 initially. Or rather, since they're going to move slowly, we're going to approximate this to be the case all the time and see what happens to the geodesic deviation equation. So if u only has a time component that is equal to 1, this u picks out the component 0 there, this u picks out the 0 component there, and the u's are both 1 for that. So what we're going to be left with is that x dot mu is equal to r00 mu nu x nu. So we also know how to compute now these components of the curvature. We can compute them in the weak field limit. So our gravitational wave we considered in the weak field limit. So we can compute now the curvature components. I'm going to compute this curvature component in the weak field limit. And if you do that, you first charge your pen. We're going to be able to express this in terms of the metric perturbation, which means that we're going to be able to express it in terms of A. Because again, we have now assumed that we are in this kind of plane wave solution. So what we will find if we do the maths here is that this is going to be 1/2, and then we're going to have d0, the second derivative in the time direction of h mu nu. And here we have made some assumptions, or rather we have used our assumptions since earlier, such that h0 nu equals to 0, and this is because the amplitude a0 nu was equal to 0. Okay, so if we insert this now, what we will find is that x dot mu is going to be equal to 1/2 x lambda a mu lambda, and then the time derivative, the second time derivative of e to the minus I kx. But this is something that you can, in principle compute, right? So what we can do now is that we can solve, rather let's insert that. So what we're going to do is the following. Okay, so let me do the following. Let me use x cross equal to 0 and a plus equals to, well, something non-zero, so that I only have one of the polarizations. If I do that and I write down the equations for x dot 1, that's going to be 1/2 x1 a11 dt squared e to the minus I kx. And if I do the same thing for x dot 2, it's going to be minus 1/2 x2 dt squared e to the minus I kx. Now I'm going to work in a limit where x does not change very much, because we have already assumed that we are in a weak field. So then this essentially tells us that if this is approximately equal to 1, and we have a small perturbation to that, we have a second time derivative there, this is approximately constant, and we have the second time derivative there, so we can immediately pick out what the correction, what the perturbation to x1 being constant is. So this is going to give us that x1 is in essence going to be 1 plus 1/2 a plus, which is this a11. There's an a22 missing here in this equation. No, it's actually a plus in both cases, sorry. So that's where the minus sign comes from. There should be a plus sign and a22 there, but since that is minus a plus, that's what we have there, and a11, that was just a plus. So what we find is that we get a half a plus and then e to the minus I kx here. And in a similar fraction for x2, we get 1 and then, well, some initial, we also need some initial condition here. So x1 at 0, whereas x2 is the same thing but with a minus sign. So minus a plus e to the minus I kx times x2 at 0. So what does this mean? Well, it means that if we look at this now, x1 for some times that are not 0, we're going to have some kind of oscillation in x1 with the amplitude half a plus, and it's, since we have a plus here in x1 and a minus in x2, the phase of these oscillations in a1 in x1 and x2 are opposite. So this means that if we look now at the xy plane, so we look at the xy plane, and we look at the point in the xy plane at time t equals to 0, and then we take some points here that are displaced with respect to this black point. So this would be the displacement vectors, and we look at how the displacement vectors essentially evolve with time, as long as all of those points are moving along geodesics. So if we move on to well, let's move quarter of a period. So that's going to be t equals to the period divided by 4. So we have this original point, but the displacement vectors for the points which are displaced in the x direction, so the 1, they are going to have increased. Let's say that we choose the amplitude such that they increase. So we're going to have those over there and over there. So if those increase, then the amplitude in the y direction was opposite, so the displacement in the y direction is going to have decreased, which means that we have those there. So if you kind of imagine now that we draw a ring here of points in the xy plane, that's going to now have been distorted to become an ellipse. If we continue moving on, so we move further to t equals half a period, then both of those oscillations are going to have gone back to the original state. So we would just copy this state here. We would have something like this at this point as well. And finally, let's look at when the time is 3 periods over 4. Then instead we have come to have the x direction in the phase such that the displacement in the x direction is minimal. So we would have the point, and we would have the x displacements now minimal. And since the y displacements are out of phase with that, or in complete opposite phase to that, they would be here and here, and the ellipses would instead look like this. Well, given my drawing skills, but you get the general idea. So this is why this is called the plus mode. It's because if you look at this circle of displacements in the xy plane, it starts off as a circle, then it goes to this kind of ellipsis, it goes back to a circle, and it goes to the ellipsis in the other direction. So if you kind of look at the extremes, you would have something like this. So you would oscillate between those two states, which is kind of this plus shape. If you would instead have looked at the A cross polarization, this entire thing, so this is the A plus polarization. If we look at the A cross polarization, you would instead have something like this. So you would have these circles, but it would be, instead the ellipsis would be in this direction. So instead of having this kind of plus, you would have the oscillations going between that state and that state, which makes this cross, which, as you can see, those two are related by a rotation of 45 degrees. Any questions? So let me, we have 1 minute left, so let me just say a little bit about, I'm not going to write anything down now. Let's see, these are the lecture notes. Let me just go to that part of the lecture notes. So here, so this is essentially what we use to measure gravitational waves. So we have this kind of Michelson interferometer, and you have here mirrors that you suspend so that they move essentially on geodesics. It's, if you look at the actual experiments, these are very these are very intricate constructions, such that you can actually make sure that these mirrors move at least in the relevant direction, in this direction, moves as if they were freely falling. And then since these arms now are in different directions, when a gravitational wave comes, now let's say that it comes from above, what's going to happen is that if we have a plus polarized wave here, then this arm is going to shrink while this arm extends, and vice versa, which is going to end up with the travel time for the light going back and forth here being smaller than the one here at one instance, and then changing as the gravitational wave passes. So this means that the interference pattern that you get in this Michelson interferometer is going to change as the wave passes. But these are really intricate experiments, and if you remember a few years back, like 5 years back, the LIGO collaboration measured something like this, which was essentially the end stage of a merger of two black holes. This was the first gravitational wave measured. And if I remember correctly, this had an amplitude of something like 10 to the minus 21. So the amplitude essentially here, the A plus amplitude, was 10 to the minus 21, which means that the displacement of these mirrors, or rather the lengthening of these arms, was less than 1 part in 10 to the 21, which amounts to basically much smaller than an atom. So this was a rather extreme measurement and an amazing feat to actually pull off.